If I put a sweater on, you will no longer see.
But then you're breathing.
You no longer see the outlines of my figure. It's as simple as that.
But then you're both. Buy
Well,
yourself a long sleeve like this, and then you can see the definition of your fingers.
it's not bad, right? All right, guys, let me share with you the whiteboard. All right, so here we go. So there we have the basic power rule. Here's what I want to do. And, you know, it would be nice if everybody in class would be writing notes, right? Instead of watching, is it Disney World? What is that? It would be nice if you're writing notes instead of watching things unrelated to class. And girls over here, if you, yes. All right, so let's continue. All right, so here's how I want to do. We're looking at this here. We're going to go ahead and look at number 1 on page 103. Page 103, and it has this following function: x squared minus 5x plus 6. And
I'm sorry for the interruption.
yes, yes,
Melanie Terrero going home.
okay.
Thank you.
So have a great day. She knew she was gonna leave. So, all right. So here's our function. I'll write f of x here. And can we go ahead and do the derivative of this? F prime of x is going to be what? 2x minus 5. And what does that derivative describe? It describes what? The slope of my tangent line. Now, here's what I want to do. I'm going to go through the trouble of graphing the quadratic. All right. Now, we're going to go ahead and this is not part of the problem, but I want to go ahead and graph it. That's what's important to me, at least a sketch. So I'm going to go ahead and write it as y equals x squared minus 5x plus 6. I know that you don't have to do this as part of the problem in the book, but I want to graph it. Got it? I can't overemphasize that's what I'm trying to do. So I'm going to complete the square because I just want to find the vertex. Y minus 6 equals x squared minus 5x. Half of 5 is negative 5, and negative 5 divided by 2. Half of negative 5 is negative 5 divided by 2. So I'll just write it over here. You're not gonna see it, but you know what? So I'll just do it over here. Negative 5 divided by 2. That's right. That's half of negative 5. And then when you square that, that's going to be negative 5 over 2 squared. That's, you guys know that's 25 over 2. So I'm going to go ahead and just write x squared minus 5x plus 25 over 4, sorry, 25 over 4. And now I do the same thing to the other side. You got 25 over 4 plus y minus 6. Now let me grab my calculator quickly because I don't feel like adding fractions right now. You know what? I have to pretend to be a teacher, so let's go ahead and add the fractions. All right. So what's 25 over 4? And I wrote 24. I don't know why. 25 over 4 minus 6. How would you add that together? How would you add that together? And let me slide the board up. You can put a 1 under 6, yes? Yes, and what will you turn negative 6 into? Yes. Negative 24 over 4 would work. In other words, you represent 6 as a fraction, yes? So you could write it like this. 6 times 4 is 24, and then divided by 4, you still have 6 there, don't you? All right, so now you're left with 1/4, right? And so you have y plus 1/4 equals x minus 5/2 squared. right? And then you just rewrite it as y equals x minus 5/2 squared minus 1/4. And now you have a vertex. The vertex is, you can clearly see it's going to be 5/2, comma, negative 1/4. And this allows me to maybe start graphing this, right? Make sense? We're good? We've done this. So again, this is not part of the problem. So I'm gonna go ahead and create an axis here. Now, this is not pretty numbers, but whatever. It's the numbers in the book, and we should be able to do it anyways. So I'm gonna go ahead and go 5/2. That's 2.5. 1, 2, 3, and negative 1/4. So right here. So this is the vertex. You know it's facing up. And then, you know, as this is a quick sketch, so I'm thinking I'm gonna go with, if it goes 1 over, it goes 1 up. And if it goes 1 up, that's 0.25 plus 1. That's like around here. And then over here, if it goes 1 over, it's 1 up. And if it's 2 over, it has to go 4 up. So 2 over, it goes 1, 2, 3, 4. Let me just do a little bit of math. 0.25 plus 4. Sorry. Negative 0.25 plus 4. It's 3.75. So it goes up to 3.75. So it'll be like around here. Something like that. Okay. And then the other side will be here. Like around here. And then obviously we know that the y-intercept here is right here. And so if I make a sketch of this, this is a parabola facing up with the vertex here at 5/2, comma, negative 1/4. Now you could have found your zeros if you wanted to, and the zeros would have been here, but that's not interesting to me and for this problem. Okay, fair enough. Are we good? So now we're gonna take a look at the derivative. Okay. So let's take a look at the derivative. So here's the derivative. I think I'm gonna do it in green here. 2x minus 5. So that we're not getting it mixed up with the other stuff. So f prime of x equals 2x minus 5. So if we look at the derivative to the left of the vertex, so let's say you pick 0 for x. If you put f prime of 0 here, you get 2 times 0 minus 5. That's 0 minus 5. What does that come out to? It comes out to f of prime of 0 is negative 5. What does that negative 5 mean? Well, I see what you're saying, but for the derivative, what does the derivative give you? It gives you the slope of the tangent line. So what is that slope? Is that slope negative 5? It means it's pointing downward, right? Agreed? How about if I pick 1? If I put f of 1 equals 2 minus 1 minus 5. Well, that's going to come out to negative 3. Is the slope negative? How do negative slopes point? They point from the left to right, they're pointing down, right? I want you to recognize that everything here to the left of that vertex is going to have, and it's really hard for me to draw. Let me zoom in because I have that ability. So every single one of these tangent lines here, right? Will have negative slopes. Does that make sense? In fact, the function on the left of that vertex is going downward always. It's decreasing. So every single one of the x values I pick to the left of that vertex will show a slope that's negative. And we say the function is decreasing to the left of that vertex. So if I were to solve this, and let's say instead of using these, I would say, okay, when is f prime, when is f prime of x less than 0? You have 2x minus 5 less than 0. And of course, it's going to come out that 2x is less than 5, which x is less than 5.5. So I know my function is decreasing. My function is decreasing for values less than 5.5. I know that. Now, when I check for f of x is equal to 0, 2x minus 5 equals to 0. Guess when it equals to 0? Guess when it's equal to 0? When x equals to 5/2. What is the slope of my tangent line at the vertex? What is the slope of my tangent line at the vertex? It's a horizontal line. At the vertex, my slope gives me 0. It's a horizontal line. This is an extremely important concept. Yes. No. You want to put it back?
No, I have it. I just don't know. Why did it be?
Because you want to generalize it.
Oh, so I.
If you want to. Only if you want to. Yes.
Isn't there an easier way to write out that function is?
Yes. Because we're starting. We're introducing it.
So I'm just like,
I know. Yeah. There's it's easier. Yeah. So this is their introduction to it. Okay, so now what do you think happens when we test to the right of the vertex? When is f prime of x going to be greater than 0? When 2x minus 5 is greater than 0. So that's when 2x is greater than 5. So x must be greater than 5/2. So you know that over here on this side, everything is going to be increasing. So just to sum up what we've talked about. When f prime of x is less than 0, we say it's decreasing. When f prime of x is equal to 0, we say it's stationary. And when f prime of x is greater than 0, we say it's increasing. Now, notice that the vertex is the lowest point. We call this a minimum. A minimum. That looks really ugly what I wrote there. That vertex is a minimum. It could have easily have been a maximum, but notice that a minimum happens when there was a change between negative, reading it left to right, between a negative or decreasing slope, right, or derivative, and then positive. In other words, everything over here was decreasing over here on this side, and then it hit the stationary point, and then on the opposite side, it was increasing. Now, stationary points could be maximums, could be minimums, but sometimes they're not maximum or minimums. They're more like something referred to as inflection points. So there's where we're at. There's where we're at. So I want to go ahead and do another problem with you with respect to this. And since we're missing so many people, we'll continue this next week. Fair enough? All right, so I'm gonna go ahead and do a problem here.
We've done something like this before, though, right? Because it looks familiar.
It looks familiar, but this is our introduction to this. We've done this.
Yeah, right?
We've sort of done this, but this is the first time that I'm kind of introducing it to you. And, you know, we'll go on more rules as we go along, but I want to go ahead and do a problem where I'm doing all of it, and we'll go from there. Fair enough?
Yeah.
Okay, so I'm gonna try to pick something that doesn't make me sad, but there's a lot of them. So let's look at 7A. This is on page 104. It says 2x to the third plus 3x squared minus 72x plus 5. Okay. And they want us to find the coordinates of the stationary points. And determine whether it's a max or min. And just to recollect on this, and this is kind of like, this is the crux of this. I think you'll like this. And obviously some of you complain, well, that was the easy problem that you did. I'm like, so what? Well, I'll go over the other ones, but you gotta try them before. So remember, stationary points are found out when f prime of x equals to 0. And then you test either side for decreasing or increasing. If it's decreasing, then increasing, that you think of it like this, and that will be a minimum. If increasing and then decreasing, you have max. That's the general idea. Now, obviously the domain here, the domain for this function is all real, so we don't have to worry about it. So 1, the domain is all reals, so I can proceed. Now, the second thing I'm going to do now is I'm going to go ahead and find the derivative of this. Y equals 2x to the third plus 3x squared minus 72x plus 5. Let's do the derivative for it. What's y prime equal to then? 6x squared. What else? Minus 6x. What else? Minus. Yep. That's our derivative. Now we're trying to find our stationary points. So y equals, number what? I'll zoom it in. I'll zoom it in. I forgot to bring my camera today. I was gonna bring a tripod today. So now I set my derivative equal to 0. Why? Because stationary points will occur, should occur, when our derivative is equal to 0. That means that at that, it's either going to be a local maximum or minimum, maybe an inflection point. So that's going to allow us to set 6x squared minus 6x minus 72 equal to 0. I got a feeling that this is factorable, but I'm not sure. Let's give it a shot. 6x squared minus x minus, well, what's that going to be? 12, no? All right. I can divide both sides by 6. And you could clearly see it's x minus 4 times x plus 3. Let me scroll that up a bit for you guys. So you could say right now, that x is equal to 4 and x is equal to negative 3. Right? So those are where our x values for stationary points should be. Now, here's what you should do then. What you should do is you have to test each side of those points. I'm going to start with negative 3. So I'll do that here on the side. So I'll make a little line here. Should I make a line? Yeah, I'll make a line. So it's just everything is not getting so bunched up. So we have this little line here. And so now I'm going to go ahead and I'm going to put negative 3 here. And I'm going to write my derivative under it. Oh, I should do it at the top. Let me do it at the top. It's better that way. So my derivative is 6x squared minus 6x minus 72. That's my derivative. I'm going to go ahead and put a value of x there. I'm going to say, well, x equals negative 3 is our stationary, right? Maybe. And so I'm going to go ahead and plug values to the left of negative 3. Can you give me a value to the left of negative 3? Could somebody give me a value to the left of negative 3? Negative 4 works perfect for me. And we're going to substitute it into here. And all we're going to care about is when we're done, we want to see what sign the derivative has to determine whether it's increasing or decreasing. So we're going to do it. 6 times 16 plus 24 minus 72. So I think it's going to be positive, but I might be wrong. But it feels positive to me. In fact, when I'm done doing this arithmetic, it comes out to 48. So y prime is 48. That means that to the left of negative 3, the function is increasing. Increasing. So now we say, okay, let's test. So here we tested with x equals -4. So now we're pick a value to the right of -3, but obviously not so far to the right that it goes beyond 4, because we got to see the behavior in between -3 and -4. So I would pick 0 because it's the easiest one, right? If you go ahead and test, we're going to test now 0 because it's to the right of -3. We have y prime equals, and I should just write on top of here. Yeah, let's do it. Y prime equals 6 times 0 squared minus 6 times 0 minus 72. And I just end up with just 72, -72. And look at the value of it. It's -72. So is it increasing or decreasing? Is it increasing or decreasing? It's decreasing. Decreasing. So now we can see that for -3, to the left of -3, it's increasing, and to the right of -3, it's decreasing. So this should be a maximum. Sometimes we refer to this as a local maximum, a local maximum. Yeah, it might not be a local maximum. It might just be the maximum. I got a feeling it's a local maximum. We'll see when we draw the graph on this, because we're going to sketch the graph for this. So now we're going to go ahead and do the same process for 4. Right? So once again, we got y prime equals to 6x squared minus 6x minus 72. In this case, x equals 4 is a stationary. Right? And I'm going to go ahead and test to the left. What's a good number to test to the left of 4, but that's not quite out beyond -3? Wouldn't we try 0 again? Isn't 0 to the left of 4? It's easy to compute. So we're going to test x equals to 0. So y prime equals to, and we already did this. We know the answer to this, but I'm just doing it. We know that when we test 0, we get -72. That was done down here. So we know that to the left, it's going to be what? Decreasing. The left of 4, it's decreasing. And now we're going to test to the right of 4. What number do you want to test to the right of 4? What's the number to the right of 4 that we can test to check the behavior of the derivative? 5. Why would you pick anything? Why would you pick 100, for example? Like that works. It's too far off. We want to see the sign here. So 6 times 5 squared minus 6 times 5 minus 72. Y prime is 25 times 6. That's 150 minus 30 minus 72. You can see it's going to be positive, right? You could tell. Right, so that's 150 minus 30 minus 72. So it is a positive slope of 48. So in this case, it's increasing. And so now if we look at 4, so we're here at 4. To the left of 4, the function is decreasing. So right is increasing. So this is a minimum. It's going to be like this. Minimum. Probably a local minimum. Local. So the next thing I want to do is I want to find a point associated with this on the original function, the actual coordinates. I'm trying to be as thorough as I can be because I'm introducing this to you. That's the next thing we're going to do. We're going to find the points, and then we're going to do a sketch. So I'm trying to be as thorough as I can because I'm introducing this to you, and it shouldn't be this cumbersome to do, and it's not. So the original function was f of x or y equals to whatever you want to do, but let's just say f of x equals 2x to the third plus 3x squared minus 72x plus 5. So I'm going to go ahead and substitute f to the negative 3. To the original function, not to the derivative, because the derivative just tells us the slope of the tangent line. And we carefully carry out that calculation so we don't make little mistakes. And if you like, you can go ahead and do f of 4 as well. And I'm going to grab my nifty TI Inspire, although I love the TI-84 better. I like it better. So I'm grabbing my calculator. Remember, guys, you have to put in the work when you get home. If not, you don't learn this. And it's beautiful things to learn, especially in the next lesson. The next lesson is quite beautiful because it's applications and they introduce some new notation. So let me go ahead and do this with a calculator. Negative 3 to the third, that's negative 27 times 2. Be careful. So that's negative 54. Negative 3 squared, that's 9. Positive 9 times 3, so plus 27. Plus, well, negative times negative is positive. 72 times 3. And then I'm going to go ahead and add a 5. And I'm getting 194. It's a really awful value. That's an awful value. Awful value. Whatever. It is what it is. And so now I'm going to go ahead and do 4 raised to the third power. And then multiply it times 2. And then plus basically 16 times 3, which is 48. Minus 72 times 4. And then add 5. And this comes out to be negative 107. So our coordinates associated with the original function, where we have the local maximums and local minimums, or maximum minimums, or stationary points, are this and this. Right? So now, even though that's not part of the problem, I want to go ahead and try and sketch this out to you and show you the power that this gives you, especially when you obviously sketch things quickly, and gives you a good idea how things work. Okay. So I'm going to make sure I got the right answers because getting wrong answers suck. Was it number 7? Okay. Guys, check my arithmetic there. Did I write the function correctly? Is that what you're getting in your calculators? Let me do it again in my calculator. Here we go. Oh, darn it. Where did I write that?
Because like, it's supposed to be 2x to the power of 3 negative 3x squared. So you go down the positive.
It's negative 3x squared originally. Okay, so then I'm gonna change it because the actual problem in the book is plus. So I'm gonna just change this to a negative. Like that. And I originally did it with a negative. Yeah, I did, didn't I? Okay, all right, whatever. Okay, so now let's fix it then. But in the book, it's positive, and so whatever. Okay, so let me write on the top here. I see what I did. When I rewrote it, somehow I wrote the negative. So let me just change it and let me say, I'm gonna write similar at the top for the notes similar because I changed one of the signs. Okay, it happens. All right, so then that means that these values are different, aren't they? So let's go ahead and fix that. So, all right. Let me see if I can fix it. So we got negative 3 squared. That's 9. 9 times 3. Negative 9 times negative 3 squared. So okay. Let's do it together then. Let's just take our time. So 2 times negative 27 minus 3 times 9. Negative 72 times negative 3. Plus 216 plus 5. And so 27 times, sorry, negative 27 times 2 is negative 54. So we have negative 54 minus 27 plus 216 plus 5. So negative 54 minus 27 plus 216 plus 5. That's 140. So we have 140. And I will do it to the other side as well. 4 raised to the third power times 2 minus 3 times 16 minus 72 times 4 and then plus 5. So now I'm getting another awful number, negative 203. Okay. So now we're gonna sketch this. So this is not cool, but whatever. This is 50, 100, 150, and I gotta do it in the opposite direction. Let me scroll it upward so you guys can see. So assuming I didn't make any arithmetic mistake with the calculator right now. You got negative 50, negative 100, negative 150, negative 200, negative 250. And I'm gonna go, this is not the best scale, but 1, 2, 3, 4, negative 1, negative 2, negative 3, negative 4, 5. Okay, so for negative 3, we have negative positive 140. So I'll put the dot like up here. This is negative 3, comma 140. And then for positive 4 is negative 203. So that's like down here. So this is positive 4, comma negative 203. Now, if I look at the work I did previously, when I tested the -3 out, it told me that the function was increasing on this side and then decreasing on this side. Now, I know for a fact, if my y-intercept for this function is actually 5. So I know that this here is 5. So when this function comes back down, it should cross 0,5 here on its way downward to here, and then goes back up. That's a quick sketch of this function. It's increasing on this side, stationary right here, decreasing, stationary, increasing. Okay? That's what it should be doing. Okay? So if I come here to my decimals calculator, my lovely decimals calculator, I have to sleep too. I have to watch TV, and I have to play Assassin's Creed. So, and then I have to play Minecraft with my daughter because I know she's going to ask me. And then it's her rules because it's not. It can't even be my rule. It's her rules. So if I write here 2x raised to the third power minus 3x raised to the second power minus 72x plus 5. Did I write it right? Look how awful it looks. So here we have this guy, -3, 140. And here we have this guy, 4, -203. But let me make it look prettier because it looks awful, doesn't it? Oh, no, not there. I don't want to do that. No, don't do that, done. Where's my, doesn't this leave me choose like, no, I don't want that. Oh, then where should it be? Would it be here? Yes. I will go ahead. X-axis, I want to restrict it to up to 10. And -10. Because we want to make it look different, right? Come on. I think they did a great job with this. And then I'm gonna go ahead and increase this to 200. And then this could be, yeah, that looks better. You see it? Make sense? This is a very powerful tool for those of you who are not in class. Like, I can't see anything but brightness. Imagine if I drop my tablet right now. You can't see, it's too bright. There, sort of. No, there. Whatever. It's there. You see the power that this has? Now, it took me quite a while to do it, but I want to give you one more tool that would make this a lot simpler. There's something called the second derivative. And the second derivative will allow you to determine this maximum and minimum like in one shot. Let me show you what I mean. Only if you're careful. So Hey guys, I'm pretending to be a teacher. Look at this. This is what a teacher does, right? They pretend to teach. Yes, but be careful. Many people have used it. It's become radioactive. So number 4, here's just something I want to discuss. What was my f prime of x? If we go back up, I'll do it here. It was 6x squared minus 6x minus 72. Now, if I take that derivative, I write it as f double prime of x equals 12x minus 6. I have the derivative of my derivative. Now look at this. I'm gonna put f of double prime of -3 equals 12 times -3 minus 6. And this comes out to -36 minus 6. And I don't care the exact answer comes out, but what I got here was a negative value. And if your second derivative has a negative value, it implies negative concavity. This means negative concavity, which negative concavity looks like this. Therefore, local maximum or maximum. So we could have done this in one shot. We wouldn't have to test on each side of -3. We could just done the negative derivative, and the negative derivative would have shown us, hey, look, I must be, for -3, I have to be a maximum because my concavity, what the second derivative measures is the concavity. And now I do it for 4. 12 times 4 minus 6. You can clearly see it's going to be a positive value. And a positive concavity looks like this. And so that's going to be a local minimum. Does that make sense? Let me scroll that for you guys. And you can do this. You just have to practice and believe in yourself. It's just practice. Make sense? So I'm gonna leave it at that. And we're missing so many students. Where are these students? They just decided not to come to school today? It's like, what's the world coming to? Let everybody can see the class. Wait. None of